So now we're in the last group of structures for the carbohydrates. We are going to look at the structures of the polysaccharides. And remember, I told you that in plants, you have amylose and amylopectin. Those are the two polysaccharides that are considered starch. So every time you're biting into a piece of bread or a bagel or a potato or pasta or whatever, anything that has starch in it, you are eating both amylose and amylopectin. And then the other plant polysaccharide we said is cellulose. So that's the fiber, all your vegetables and fruits with the skin on them, that's all the cellulose. All right. There are other polysaccharides out there. We're just not going to worry about them or deal with their structure. These are the only ones I need you guys to focus on. All right. So remember what I told you about amylose. Amylose is thousands of glucoses, and they're all hooked up together, alpha-1,4, alpha-1,4, alpha-1,4. Obviously, we're not going to draw out 1,000 glucoses. So what I do is I draw out 3 glucoses, and I connect them alpha-1,4, and then I do dotted dots on either sides to basically say, et cetera, et cetera, et cetera. So this top one, ignore these two right now. Let's focus on this top one. Can you see that it looks just like maltose? Do you remember how maltose was just two glucoses and they're hooked up alpha-1,4? Well, now I've got 3 glucoses and they're hooked up alpha-1,4, alpha-1,4. How do I know they're glucoses? Because of the way this is pointing down. If it was pointing up, it would be galactose, remember? So notice that there's really no carbon 1 at the end. There's way at the end. Remember how I told you carbon 1 that could be an aldehyde and open up and become an aldehyde and close and flip alpha and beta? We don't see any of that. That's way at the end over there. So all you do is when you're looking at amylose, you just see a bunch of glucoses hooked up alpha-1,4, alpha-1,4, alpha-1,4. And you know that there's going to be no galactose, no fructose in the polysaccharides. So if I have a structure and you see more than 2, you know you're dealing with a polysaccharide. So it's going to be up to you to determine what is it. Is it amylose? Is it amylopectin? Is it cellulose? Or is it glycogen? So you see a bunch that are hooked up alpha-1,4. This is for sure amylose. Okay? And have you heard of the enzyme amylase? You've had that in biology or in anatomy and physiology. The amylase enzyme, you have the amylase enzyme in your saliva. There's salivary amylase, and then you have pancreatic amylase. That helps with catalyze the hydrolysis, the breakdown of amylose and of amylopectin when we get to that over there. So we have the enzyme to break these bonds, all right? So amylose is broken down with the enzyme amylase. This is a neat little thing. Try this out at home. Get a saltine cracker and just put it in your mouth and just keep it there. Don't chew it, don't swallow it, and don't talk. Just sit there with the saltine cracker in your mouth for a while. You will notice after a while, well, obviously it's going to get mushy, but it starts feeling a little sweeter. What is happening? Your amylase enzyme is beginning to hydrolyze those glycosidic bonds. Now you're getting free glucose and free maltose, which are a lot sweeter than the big bulky amylose. All right, just a fun thing to do. All right, the next one that I have here, you'll notice they're all glucoses also, but can you see that this is a beta? Beta-1,4. So amylose is all alpha-1,4 glycosidic bonds. Let's write down the word glycosidic bonds. Which is the one that had a bunch of glucoses that were all beta-1,4? This is cellulose. That's plant fiber. So this is cellulose. And this is beta-1,4 glycosidic bonds. How did you know that it was beta 1,4? Because you can see it. See, it's pointing up. Beta 1,4, beta 1,4, and then et cetera, it's going this way and this way. All right. Again, thousands of glucoses, all beta 1,4. All right. Our body does not have the enzyme to hydrolyze this. We do not have that enzyme. So this comes down into your colon or your large intestine, and that's what gives bulk to your foods and helps you eliminate it as a good bowel movement. All right, very important for gut health. All right, but we do not digest this. We do not break this down. Why? Because we don't have the beta 1,4 enzyme breaking capability between two glucoses. We have one for galactose and glucose, the beta 1,4 for lactase, most of us that are not lactose intolerant, but those of you who are lactose intolerant, you don't have that lactase enzyme. Anyway, so let's get back to this. This is amylose broken down with amylase. This is cellulose. We do not break it down. We do not hydrolyze it. We don't have the enzyme. Difference between amylose and cellulose, you need to be able to see the difference. These are all alpha 1,4s. This is beta 1,4. Okay, so draw them out on your index card so you can see the difference there. This big complicated thing over here, can you see what we've got here? They're all glucoses. You see an alpha 1,4 here, alpha 1,4, alpha 1,4, but look over here, look what this is. This is carbon 1, excuse me, and this is carbon 6. See, this is carbon 1 of this chain, and this is carbon 6 from this chain. So it's like you've got two chains on parallel to each other, and you have an alpha 1,6. So with amylopectin, this is amylopectin, you have alpha 1,4 and alpha 1,6. Where do we find amylopectin? It's part of starch. Remember, starch is about 75% amylopectin, 25% amylose. Every bite of starch, you're getting a mixture of both of them. All right. How do you recognize amylopectin? Bunch of glucoses, you'll see an alpha 1,6 and an alpha 1,4. If I tell you to explain the difference between amylose and amylopectin, you'd say, well, they're both starch. They're both made up of thousands of glucoses, but amylose has no branches. It's all alpha 1,4. Amylopectin has branches. There's an alpha 1,4, and then there's a branch at alpha 1,6. With amylopectin, this is just an approximation. It's approximately every 20 glucoses or so, you'll see a branch coming out. Okay? Now, I'm not going to redraw it, but now we're going to pretend that this is not amylopectin. We're going to say this is glycogen, because glycogen looks exactly the same as amylopectin. The key difference is that it's more highly branched, but you can't really show that in a structure. So if amylopectin is branched every about 20, glycogen is branched every about 15 or 13 or something. Again, all approximation. Key thing to know, if you wanted to know the difference between glycogen and amylopectin is found in plants, glycogen is found in animals and humans, any animal. Where is glycogen located? It is in the liver and the muscle. That's where it is stored. It is the storage form of glucose. All right. So we're going to say this is glycogen. All right. So now we drew amylose, cellulose, amylopectin, and glycogen. I like to ask my students, why do you think we can't store a lot of glycogen? Like, how come we can only store a little bit of it, but yet we can store a ton of fat? We can fill our fat storing cells, fill them up with fat. We can just make them 50 times their original size. But we can't with glycogen. Like, how come we can't store a bunch of glycogen in our muscle? You know, those ultra athletes that not just run a marathon, they'll do the Ironman, you know, they'll do the swimming and the biking and a marathon, or the ultra marathon ones that do like 50 miles of running or crazy 100. They would love to be able to store a ton of glycogen in their muscles, but they can't. Why do you think that's the case? The key is that glycogen has a whole bunch of OHs. And these OHs, they can hydrogen bond with water. So we didn't really talk about hydrogen bonds, but they're very important in biochemistry. The hydrogen bond, if you remember it from intro chem, occurs when a hydrogen is bonded to an oxygen and then attracted to another oxygen. Well, water can hydrogen bond, and all these OHs can hydrogen bond. So they attract so much water, your liver and your muscles would become huge like this, filled with water, and it would burst. All right, so we unfortunately can't store a lot of glycogen. The reason we can store a lot of fat, you're going to see when we do the lipid chapter, there's no OHs. It's just CH2, 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 so there's no hydrogen bonding there. Okay, just a little bit of interesting tidbit here. All right, the last video that I'm going to do is going to be about some reactions. We'll talk digestion, and we'll talk about reducing sugars and non-reducing sugars, and that will wrap up the carbohydrate chapter. Okay, good.